Dr. Tebaldi is a senior scientist with the Joint Global Change Research Institute, PNNL, and her research interests center around the analysis of observations and climate model output in order to characterize observed and projected climate changes and their uncertainties, with the goal of making this information useful for modeling and estimation of socioeconomic and environmental projects. She has published papers on detection and attribution, on extreme value analysis, future projection at regional scales, the use of multiple climate model projections, benefits of mitigation, and impacts of climate change on agriculture and human health. She has participated as a lead author in the past two cycles of the UN's Intergovernmental Panel on Climate Change Assessment Activities and was a chapter author for the US National Climate Change just released. She has co-chaired Scenarios MIP, an international activity that designs future projection experiments for climate models to undertake in coordinated manner all over the world. She also collaborates with Climate Central's Climate Science and Impacts Group and provides scientific oversight and advice on organizations program. She has a PhD in statistics from Duke University and was a researcher at National Center for Atmospheric Research for most of her career before moving to PNNL in summer of 2019. I would just like to request everyone to mute themselves during the talk and ask any questions after the presentation. And with that, I would like to give the floor to Dr. Claudia. Thank you very much, and the floor is yours.
Thank you, Jade, and thank you for having me here. It's a pleasure to talk to you today, and hello, everybody. I'm going to start right away. I'll share my screen, and please let me know if you see my presentation in full screen mode. So I am going to talk about emulators today, and emulators applied in the general area of climate change research for uncertainty characterization and integrated modeling. I have a large list of collaborators. I have a slide at the end of the talk that recognizes that a lot of this work is actually work done by collaborators of mine, mostly. I was not really sure if the audience was familiar with the general area of application that I'm talking about. So I thought I spend the first 5 or 10 minutes giving you the big picture within which the application of emulators is relevant, at least what I'm talking about. And so I have this simple schematic here that highlights the three major components of the problem and the way we go about modeling it. So we're all familiar with the problem of climate change and the fact that it affects the climate system, the physical climate, and we use models to represent that system that have very high level of details. They are very complex, at least those that represent outcomes at the regional scale that are relevant for impact modeling. Of course, the problem doesn't stay within the climate system. It reverberates across systems that are relevant to humans, like agriculture, human health, water resources, you name it. So we usually take the output from these climate models and we feed them into impact models that tell us something about the outcomes, the risks of climate change. And then we usually, at least when I use the formula integrated modeling in my title, I was referring to this idea of actually closing the loop and therefore using what impact models tells us about the consequences of climate change for the human system, the economy, population. This human system in turn will influence the climate system because how economy evolves, how people move, what they do, how they produce the stuff that they need to produce, the choices in mitigation that they take will influence the climate system through the amount of emissions of greenhouse gases and other relevant gases and land use changes. Okay, so where do the emulators that I'm talking about become relevant is in this section of the problem. So as I mentioned, we have these impact models that take what climate models simulate and translate it into impacts, risk. And our impact models have become more and more sophisticated. So they need the kind of information that a climate model produces. So they need information at the regional scale, often at high frequency, temporally, like, daily, perhaps monthly information. And they need it for a whole host of variables like temperature, precipitation, winds, humidity, solar radiation, you name it. So to feed this kind of information into impact models, of course, we can use what climate models produce. But the issue is that sometimes we want to do this for many more scenarios that are available already from what climate models have run. So this very rich type of information that comes from climate models is usually available only for a few scenarios of future greenhouse gas emissions. And we may have ideas in mind where we want to test the consequences of a different scenarios that hasn't been run by climate models. And that's where emulators come in, because emulators are those solutions that take the place of climate models. They are climate model surrogates that still can produce this kind of information that at this level of comprehensiveness, but they do that in a computationally efficient way. And why is this important, this computationally efficient aspect of emulator? It's because when we consider where climate models can be run, this is the picture that we should keep in mind. So this is a supercomputer. It's at NERSC, which is the National Energy Research Scientific Computing Center in the Bay Area. And these are the kind of computers that are needed if you want to run a climate model. So you understand how expensive, how long it takes, but mostly how expensive it is to run a climate model. However, when we think of what it takes to run a new scenario of future greenhouse gas emissions, the picture is very different. So where I work, we have a model called the Global Change Analysis Model. Is a so-called integrated assessment model, where the various components of the human part of the problem, water, energy, land systems, and socioeconomics, like the evolution of the economy, the growth of the population, are all represented in a consistent way. And despite this, these models are very efficient computationally. And so you can run this kind of simulations that produce a new scenario of greenhouse gas emissions in the matter of minutes on your laptop. The result of that is that the community, the scientific community out there that thinks about the possible future pathways of emissions that will be plausible, that we would need to follow to achieve some targets like the 1.5 or 2 degrees target, that community can produce thousands of scenarios. And you see here in this plot, many, many gray lines. These are all the thousands of scenarios that were produced, I'm sorry, for the last phase of a CMIP, except only those colored lines were run by climate models, exactly because it's so expensive to run climate models. Nevertheless, one could be interested in exploring what are the climate consequences of many different scenarios that are not just those colored lines. Now, I'm having trouble advancing my slides, but hopefully it won't take too much to learn it. So the other aspect of the problem that comes to our help here is that translating these scenarios into global average temperature takes even less than a few minutes on a laptop. We have so-called simple climate models, and here at GCRI we have one called Hector, but the most famous ones perhaps are Magic or FAIR out there. What these models do, still from a process-based perspective, take emissions and land use actually also, and translate those into radiative forcings, which is the quantity that tells us what the imbalance of energy coming in and going out from the sun is over the course of the century, and then translate this radiative forcing into global temperature. So just to recap, it's very expensive to run climate models. On the other hand, it's very cheap to come up with interesting scenarios to explore, and it's very cheap to translate those into global temperature. So now the last step that I have to tell you about is these other fairly convenient things that was studied and characterized and actually exploited pervasively in the last IPCC report. The interesting aspect here is that for many quantities at the regional level, even at the high frequency level, temperature, precipitation, soil moisture, these are the ones that I have here, but many others that are relevant to our impacts, there is a very strong relation between what happens at the regional level to these quantities and what the global temperature is. So here is where emulators come in, because you can devise, sophisticated or less sophisticated method to relate global temperature that you can get cheaply to outcomes that are more relevant for impacts. So what I'm showing you here are examples of the strong relation between global temperature and three variables. And the idea here is that the columns here correspond to different levels of global warming, 1.5, 2 degrees, 4 degrees. And the pattern tell you what happens to surface temperature, precipitation, and soil moisture at those levels of warming. Now, what is interesting to note here is that if you look at this pattern, you see that the relative, warmer, cooler, wetter, drier areas don't move around the world with the different levels of warming. So the patterns themselves stay fairly constant, of course, to a first order. What changes is the intensity of the pattern. And so here is where, this relation between global temperature and local things can be exploited. You can imagine you have a lot of simulations for those few scenarios from climate models where you can get this type of information, and you can have the global temperature information at the same time. So you can use, statistical models, machine learning models, or a model that I'm going to present you that amounts really to patching together existing information to emulate what would come out of a climate model. Okay, so I'm going to next talk about our solution to the emulation problem that we call stitches. So here is where we start from. I told you, usually you have a new scenario that you can characterize in terms of global temperature. Somebody has created, a new pathway of greenhouse gas emissions and land use, and you have used a simple model to say what that means in terms of global temperature, but now you want to say something more about, local temperature, local precipitation, wind, whatever. So you start from this new trajectory, and you know that if you go into the archive of the CMIP project, you can find a lot of simulations of existing scenarios for which you have not only global temperature, but all the information that you need. So we go and we choose a model that we want to emulate, and we look at what that model has run and has saved in the archive in terms of global temperature. So here is a case where we have a model that actually ran 5 scenarios. None of those coincides with the one that we want. But those 5 scenarios have been run actually with a lot of replicate, or what we call initial condition members, slightly perturbing the initial conditions and getting a slightly different realization of weather along the same general climate pathway. So we have all this stuff available. Unfortunately, nothing that really coincides with our scenario, at least from the middle of the century onward. But we're going to split the problem now into pieces. And that's where the name stitches comes in. So instead of being concerned about replicating the whole scenario at once, now we are concerned about replicating pieces of the scenarios, and we choose to do it for about 10 years, 9-10 years of periods at each time. So what we do is we split our target scenario into pieces, and then we split what's available into pieces. And now the idea is that for each of these windows, of the black windows, we are going to find an existing window, an existing experiment that replicates that window as close as possible. And of course, I can show you how that happens from a qualitative point of view. So, if you see my pointer, if I want to replicate this window here, I can probably find a window that is similar and I'm going to tell you exactly what I mean by similar in a moment. So let me change this display into a different space. What we want to use to match those windows are 2 pieces of information: how warm it is in that window and how fast it is warming in that window. So the median temperature anomaly in each window and the rate of change in the window. These are our new quantities that characterize each of those little windows. And now each of those little windows is a point in this space. And the colors here are the same as the ones that I had here. So the dark red scenario, those windows that you see there are, represented by these points. And I'm showing you here a lot of points because I have a lot of those scenarios. I don't know what that line is right now. I must have touched something, sorry. But this is the same data that I had in this picture, except in this new space. And now you can guess what my target scenario is going to be in this representation. It's going to be simply a series of new points that correspond to the anomalies and the rates in all the windows of my black line, these ones. Okay, so now the problem becomes to match each of these points with its nearest neighbor in this space. And we can do that, and we can find then for each of these points its closest existing window in the archive. And what that translates to is, and I wish I could eliminate that thing, but I hope it doesn't disturb you too much. What we come up with then is what we call a recipe, where for each of the target windows, we have like a lookup table that says, if you want to emulate that window, go and take that experiment, that ensemble member, that time window, which may not coincide with the same time window as your target experiments. And you go through and you have this entire sequence of pointers. And that's why we called it stitches, because now we are going to stitch together these windows and recreate my new scenario, my target scenario. Now, what I want to underline though here is that I'm doing this all in the space of global temperature, because that's what I have, right? I have a new scenario that is only characterized by global temperature. But the point here is that because of what I told you before, that there is this strong relation between global temperature and other quantities, I can go into the archive and take those windows and those experiments and extract everything that that model has saved during that time and that experiment. So I can stitch together, other variables like temperature, precipitation, winds, humidity. I can take output that is not, annual, at that annual frequency. I can even extract output that is at the daily frequency or monthly frequency. And so our recipe here delivers a series of, quantities, anything really that we need, with a couple of caveats that I'll get to in a moment, where, the sequence is now not a sequence of global temperature values, but it's a sequence of grids with the same resolution as what was native to the model, and possibly frequencies that are as high as the model has saved. So here are examples, just as a representation of the fact that I can get out monthly temperature, daily precipitation, sea level pressure, humidity. And of course, I can use information from this grid at the grid point level. So our organization is in College Park, Maryland. So I use the location over the grid of College Park, and I show here a time series from the climate model at that location. And you look at this series, and I hope you don't get, the impression that these are Frankenstein monster type of series, but in fact they are, in the sense that they are the result of stitching together 9-year window from different experiments, possibly different sequences of years. But the point is that the connecting thread here is that global temperature that ensures consistency of this sequence. So we are getting to the end of this part. We have a little motto for our Stitches emulator, and the motto is, if the ESM has saved it, Stitches can emulate it. And it works because most of the variables that impact models need behave in synchronicity with global temperature. So stitching together discrete windows independently of the previous path is okay. It's like, the global temperature becomes the sufficient statistics here. So when you condition on that, you can forget about everything else. So if the global temperature satisfies the consistency requirement, then these variables do as well. And so if the scenario is close enough to existing ones, it can be emulated. And of course, that close enough has to do with that two-dimensional space that I showed, those dots, because like the first point of the caveat says, if the scenario that I want to emulate is above anything that is available or below anything that is available, you are in a part of that two-dimensional space where you don't have nearest neighbors points. You can always find the nearest neighbor, but it's probably very far, and so you would have a very different behavior there than your scenario that you are targeting. And now for the most important caveat here. So I've been very, positive in saying you can emulate anything, but of course there are variables or metrics that could not be faithfully emulated here. One major example is sea level rise. So sea level rise is a quantity that acts as an integrator of what has happened in the past. So it's a time-dependent quantity and therefore cannot be emulated this way by patching together pieces that don't have the same history as the target scenario. And then the other obvious example is mega droughts. So I told you that we split things into pieces of 9 or 10 years, and that choice is a little bit of a trade-off where you want to have enough pieces to have a rich basket from which to sample, but you don't want the pieces to be too short to lose the coherency that, for example, comes in a time series of temperature precipitation from things like ENSO or other, slightly lower frequency characteristics. So we chose this 9 to 10 years window, but if we are interested, for example, in mega droughts that we know last much longer than 9 to 10 years, then our emulator would very likely split them into pieces, and we couldn't characterize them accurately. But for many other variables, this solution works. And of course, I have been very, hand waving here, but we have a paper accepted where it's in Earth System Dynamics, where you would find rigorous validation of the fact that the time series maintain a coherency. You couldn't find, in most cases, the splits that I showed you in those plots. And the behavior of the variables is indistinguishable from the behavior of variable that comes from a coherent simulation from a climate model. And we also have software available on GitHub, and we have a paper that is about to be published in JOS, where the software is described if people want to play around with this method. But my point in showing you this is, of course, showing you our work, but just to raise the awareness of the problem of emulation and the possible interesting ways that one can dream of emulating this climate model output. And in fact, the second example I have here is a different kind of emulations that attacks the problem from a different perspective altogether. So I call it bottom up in the sense that the approach here has to do with learning the statistics of the climate model output by using what's available, and then generate new samples altogether once those characteristics are learned. Differently from our teacher's approach, where we cannot really create anything new, we just patch together existing pieces. And when creating something new becomes important is when you are interested, for example, in estimating the characteristic of extremes from climate model simulations. And again, for most scenarios, you don't actually have a lot of replicates. So you don't have the statistical power to characterize extremes, and even less to characterize changes in extremes. So if we can train a cheap emulator to learn the characteristics of daily temperature or daily precipitation from existing scenarios, existing simulations that may be, just 3, 4, 5 replicates. If we can train the emulator to replicate the same spatial and temporal characteristics of model output at the daily scale, then we can use the emulator to generate a lot of samples. And with those, we can estimate the characteristic of extremes in a much more robust, precise way. So the work that I'm presenting here now in a much quicker way is work that I'm doing in collaboration with machine learning experts at Western Washington University. So of course, people have attacked this problem of learning the statistical characteristics of climate model output with elegant statistical models, especially spatial statistics models like Gaussian processes and other types of spatial models that that really exploit our statistical modeling approaches. But being 2024, of course, machine learning is lurking there, maybe more than that. And we embrace it and we see what we can do by deploying one of these models on this problem. So my collaborators, and again, I'm presenting this in a very superficial way. I'm hoping to just give you an idea of the approach. And once again, it's not to teach you the approach, but just to spark some, hopefully, interest in the problem itself. So my collaborators are in the computer science department of Western Washington, and they got interested in applying so-called diffusion models to the problem. And diffusion models, from what I understand, are very good at learning the characteristic of videos, video sequences. So they thought that the problem of replicating a sequence of daily output from a climate model was similar to learning, how a video, a series of images in a video behave. And so they decided to use this framework, diffusion models, to learn the distribution, both in space and in time, importantly, of daily output of temperature and precipitation. And the way the model works is in the training phase is to start from a sequence of daily output from climate models and recursively degrade that sequence of pictures, of the pictures individually, but maintaining, the coherency of the time evolution by adding Gaussian noise to these images, and doing that over and over and over again until you're left with, something that is indistinguishable from Gaussian noise. And once you've done that, you have trained the model to go from a coherent set of pictures to just Gaussian noise. And you can invert the learning process and now give the model Gaussian noise and ask it to replicate your coherent pictures of daily temperature and precipitation. So that's what happens in this model. Here is a schematic again of the fact that we start from daily output. We add Gaussian noise, we create noisy samples. The net here is the core of the diffusion process. And then once the diffusion process has learned how to go from coherent to noise, we feed it noise and we get back the daily output. The fact that there is a monthly average map here is that we make our life a little easier, possibly because we don't have the computer resources that other organizations may have. And so we make the problem a little easier by generating, by learning and then generating this daily output by conditioning on their monthly mean. So the idea is that you may have monthly means existing from the climate model, but now you're able to generate sequences of daily quantities consistently with those monthly means, but still different from one another to create a different realization of daily extremes. So a little bit more details, but it's just we train the model on a specific climate model, but this is a method that can be applied to any climate model. We use precipitation temperature data. For now, we are working with them separately, but we hope to have a model soon that can generate them jointly. For many applications, that's important. The model is trained using only 6 realization of daily outputs, spanning the whole trajectory from pre-industrial to the end of the century. Actually, 4 are used for training, and then 1 for validation and 1 for test, and I will explain what that means in a moment. You know, the model treats as a single data point a stack of maps. 96 by 96 happens to be the resolution of this climate model for 28 consecutive days. And so those are considered like the frames of the video for the model. And then, as I said, the model is trained, and we can generate now new daily sequences on the basis of an existing scenario that the diffusion model hasn't been trained on. So we trained on a higher scenario actually, and then we test the results on a scenario that the model hasn't seen, but for which we have monthly means. And of course, we also have the daily output, but that is going to be used for validation. And what we're going to look at are, you know, characteristic of the daily output, but also some metrics that have more specifically to do with extremes. And we will use, you know, maps and histograms and tests to validate the output. So first of all, I'm going to show you this, which are just, you know, pictures of time series for 3 locations. We do this on the whole globe, of course, but I'm just extracting here 3 locations that are very different from each other. Something in Russia, something over Hawaii, and the grid point closest to Melbourne, Australia. And for each of these, I have 3 time series, 3 time series, time 2, because I have those for temperature and for precipitation. The point here is to show you the generated output, the test, and the validation. And what these 2 are, the test and validation, are just 2 realizations, the ones that we kept aside from the model itself. So both of these 2 are model output for the same, you know, scenario, except they are slightly different because of initial conditions. And so they give you a sense of the noise in the system, so that, you know, differences between the generated and one of these, we hope, would be not noticeably different from the difference between the validation and the test that are both, you know, honest to God climate model output. And so, of course, this is just at the inspection. Things look good. They look similar across the rows. They look very different across along the columns, of course, because these temperatures and precipitation time series are very different depending on where you are on Earth. And then, of course, we can apply more rigorous validation by looking at the characteristic of the autocorrelation and partial autocorrelation function. You have temperature and precipitation here, and you want, of course, things along the rows to look similar. Things across, of course, look different because they pertain to the different locations. And now, I told you this, and the other things we do, as I mentioned, is not just look at the behavior of daily quantities, daily time series. Of course, if that is good, we hope that everything that comes of those daily quantities is going to be accurate. But we do validation on specific metrics of extremes. For example, the average length of what we call hot streaks, which are the periods of consecutive days above a certain threshold, above, in this case, the 90th quantile of climatology. We look at the value of temperature when the day is above the 90th quintile. We look at the length of a rainy spell. We look at the average quantity of rain that comes down during a rainy days. And we compute, average behavior of these metrics over time and over space, and we compute errors between the generated and the test set, and we make sure that that is not radically concerningly different from the difference between true realization from the models, which is in most cases the case. And we do even, KS test for the distribution of these quantities at the grid point level. So that's how we go about both modeling and validating the diffusion model. We are fairly happy that we are getting an output that looks very much like the output of the climate model itself, and that allows us to generate additional realizations of daily temperature and precipitation conditional on monthly means, from which statistics of extremes can be estimated more precisely and robustly. And now I'm going to talk for another couple of minutes just about a very different type of emulation. I actually saw Lindsay that is connected, and so I'm excited to have her here because she can answer questions about this if they come up. I've talked so far about emulators that have to do with recreating climate model output for the use in impact research. So we want these methods to just take the place of our climate model and produce the same kind of things more cheaply. This application here is instead a more internal application to the climate modeling community. And it has to do with the fact that climate models are very complex and have very many parameters that need to be tuned to produce an optimally behaving simulation. So anything that we cannot represent directly on the grid of a climate model needs to be parameterized, needs to be approximated. And these parameter values are estimated to our best from observations or from finer process models, but they have also a lot of uncertainty. So there are many different values for these parameters that are still possibly good, but we don't know how to set them in an optimal way because, again, the climate model is very expensive to run. So we can only try so many combinations of these parameter values. And we may not be lucky to be trying by chance the optimal one. So that's where emulation here comes in, which is you try as many parameter setting combinations as you can. You run them through your model. The model produces output for the current climate that can be confronted with observations. And you can use this output and the value of the parameters to build an emulator that allows you to now sample intermediate settings of these parameters and produce the same kind of output in an approximate way, of course, that you can, again, confront with observation. So if you have this machinery well established, you can now do an optimal search or a search for the optimal parameters that minimize some metric of performance, some form of root mean square error between what comes out of the model and what you have in your observations. And so you can now fine-tune the setting of those parameters on the basis of this work that wouldn't have been possible if all you had was that finite number of trials by setting parameters to this discrete number of choices. So you see here on the left-hand side a rendition of the emulator that can create this surface in this case in the space of two parameters. So for different values of the parameters, the quantity that you see here that has to do with shortwave cloud forcing in particular was extracted from the model simulation, and it's one of those green dots, but then the emulator approximates the behavior of those green dots by this nice continuous surface. And now you can actually explore what that means for values of the parameters that are away from those individual green dots and maybe in between some. And if that surface happens to be a better surface at that point than the ones that you have actually run, you can choose that combination of parameter values instead of the ones that you have tested directly in the model. So in the middle, you just see a proof that for different type of quantities, the surrogate is very similar to the actual model output. And on the right-hand side, you see, what happens to the root mean square error when you optimize the choice of the parameter, and you see that, for some cases, things are getting, in most cases, things are getting better by choosing optimally the parameters through the use of the emulator. Okay, so I think I'll stop here. And here is the important slide, which is all my collaborators, and in most cases, those that have actually done the real work. I want to thank you for your attention. This is my email in case you want to get in touch. And of course, I want to acknowledge the support of the US Department of Energy, the Office of Science, that puts the bill for our work for the most part. Thank you.
Thank you, Dr. Claudia, for such an amazing and insightful talk. And I would invite everybody to unmute themselves and give her a big round of applause.
You don't have to unmute yourself, but thank you. I'm glad
Yeah. So with that, we can begin our discussion. So anybody who
I
has
see some
questions,
familiar faces here.
so anybody who has questions, please either unmute yourselves to ask, or you can type in the chat. So uh, please go ahead. Otherwise, I mean, I can start with question first. So
Hello.
uh, yeah, go ahead.
Okay, thank you. Thank you, Prof, for your presentation. I'm Bubakar. I'm a first year PhD student. I'm also doing similar things using machine learning. But in our case, our target is observation, era 5. We are trying to map era 5 to CMIP output. What we are doing is normally downscaling, but as both are not aligned, we are doing domain alignment. We are trying to align era 5 to CMIP output. But the issue with CMIP is like not really an issue, but with machine learning, we need more data. But when we try to, what in our case we are doing is to compute quantile over 10-year period, both sides. We pick a model from CMIP, we compute the 10-year quantile, and also we use era 5 to compute 10-year quantile and try to match both in supervised manner. But the issue is like we don't have enough data.
And is the issue mostly for era 5, or is it for the model itself?
No, the model itself, because we have good results, but the model is overfitting because of a few amount of data we have at hand.
Have you tried to explore those so-called large ensembles that give you a lot of realizations for the same scenario from the same model, or do you need more than one model to do this work?
Okay. I'm at the early stage of this project, so this was the first thing we tried. But one issue we were facing is, as I said, is like we don't have enough data to really train the model.
Yeah. So there are, models that have provided more ensemble members, like those thin lines, the colored lines that I showed in my plot. That was a model that produced a lot of ensemble members for each scenarios. It's not the case for all of the models, so you may want to look into that when you choose the model that you are using to prove your method. And then there are also other type of ensembles that are not CMIP, but they are, for example, archived at the National Center for Atmospheric Research. And these are experiments that use a single model, usually one scenario or two, and then they run a lot of ensemble members, so 50, even 100. So maybe you have better luck there.
Okay. Thank you. One last thing, please. Can we have access to your presentation?
Yes, I think I'll make it available and it will be posted.
Okay, thank you so much. Thank you.
Anybody else has any questions? Please, yes, Duncan,
Duncan.
please go ahead, unmute yourself and ask.
Hey, Claudia, thanks for the
Hi, Duncan.
Hey. I was curious about this auto-calibration work you mentioned at the end. What regression do you use for the surrogate? And
Lindsay, do you want to take ownership of your work?
Sure, yeah.
Hey, Lindsay.
Hi. Yeah, I can speak to a little bit about what we've been doing. The surrogate we specifically have chosen for, we're just calibrating the atmosphere model only right now, and we've been using polynomial chaos expansion on a reduced parameterization. So just using empirical orthogonal functions and fitting independent PCEs. But we've tried everything from neural nets to random forests, etc. And we have like a full Python script that just compares them all before we choose. So
nice.
I would say they marginally perform better from a predictive sense. But we've just found that, that does all right. Now, scaling is a challenge when you introduce a lot more inputs, which we've been playing with as well. But yeah, that might be an extended answer to your question.
No, well, briefly. So, I'm curious if you've explored Gaussian process regression.
Yes, we have. Yeah, that's also one. Yeah.
Okay, nice. I think they're very similar to chaos expansion anyway. I think mathematically they're very similar. But how do you deal with, when you do the kind of gradient descent or the optimization bit, how do you deal with multiple minima?
Well, we have a very simple loss function right now. So our loss function is pretty strictly average RMSE, because that's also what is familiar to those that hand tune the model. But that's an open science question, I think, as far as how your optimal loss function and how you weight your different fields.
Right.
And that's something we've also played with, especially when you talk about using it for sensitivity analyses and things like that Claudia probably knows about too. And then there's there's just, because we have everything from spatial fields to scalar values that are part of that loss function. So definitely open question. Yeah, there it is. I can try to, it's on archive. I can send that to you.
Oh yeah, if you can pop it in the chat. I mean, I can probably
yeah, it's in the second round of reviews, so hopefully it'll be available.
Thank you, Lindsay, so much. I think this actually wouldn't have been possible without you, and that's the beauty of being old and just the bird eye view, and then you have actual people that know what they're talking about.
But
yeah, here it is.
Thank you again.
Anybody else has questions, please just unmute yourselves and ask. I can ask one question. So I mean, I was wondering if there's a difference between simulation and emulation in this case. So emulators are these software. So do they represent the entire dynamic of the climate models, or if they don't, then in that case, how can emulators help simulations, and how can emulators help things like digital twins to become better in some sense?
Yeah, so the kind of emulators that I was talking about in the first part of the talk is really a simplified surrogate for the model itself. So definitely it doesn't, it doesn't generate things from a process-based point of view, except Stitches does indirectly because it uses actually climate model segments. So everything is coherent there. But for example, the diffusion model is just a blind, machine learning model, doesn't have anything to do. That said, there is work that uses, emulators or, statistical approaches where some of the laws of physics and thermodynamics and all the understanding that comes from our science can be integrated. And there are emulators that do not worry about recreating the climate model output, but actually help the climate model to simulate, as I mentioned, things within a box that right now are parameterized a certain way with some form of approximations, and the emulators take the place of those approximations and offer a different solution to this approximation problem. So emulations, are of many kinds and of many solutions, and I just presented a couple, but there is a lot of work out there that is much more sophisticated, for example, than my own, the Stitches, where things are generated, using more understanding of the physical dynamics of the model.
All
Except
right.
the trick is, at a certain point, if you want to have all the variables that are relevant at the fine scale, at the high frequency, at a certain point, you're asking for a climate model. So it becomes a different type of climate model, but it will be of that level of complexity probably. So you kind of defy the purpose of simplification.
Okay. All right. Thank you, Dr. Claudia. If anybody still has any question, please feel free to ask. I'll stop the recording here.
Okay. Yes, you can.